Let's start section 3 of unit 8 about weak acids and weak bases equilibria. We will be calculating the Ka value or something in that equation. So we have memorized 6 strong acids, and we assume that 100% of them ionize. Apart from those 6 acids, we assume that they barely or partially ionized. So a general equation for the ionization of weak acid can be described as follows. So you have the K value and you have your hydronium. I'm putting the products as my numerator and my reactants as my denominator. Obviously, we're not going to be adding the H2O because it's a liquid, and this is what it should look like. Remember that hydronium ions and hydrogen ions are the same thing, so please don't be confused when you see either of them in the equation, like over here. These are all of my species that are involved in the reaction. Let's look at a picture of a strong acid and a weak acid. So what this is telling us that in a strong acid, we have the acid, which is HA, is just a general, name that we give to an acid who we don't want to name yet. So in this particular strong acid dissociation, we can see that we made plenty of hydronium ions. But in our weak acid, notice how only one of the HA particles dissociated and made the hydronium ion. So there's barely a difference. There's one more thing that I'd like to point out. I just thought it's important that I say it once, is that our strong acids have the halides, as in the halogens here, hydrochloric acid, hydrobromide acid, and hydrogen iodide acid. Notice that this doesn't include the halogen fluorine because it's not a strong acid, it is a weak acid. And the reason why it's weak is because fluorine is an extremely electronegative atom, and based on the Coulomb's law, remember that the shorter the radius, the stronger the bond is going to be. So it's not easy for hydrofluoric acid to ionize. Okay, let's move here. Let's look at a number of weak acids. We don't have to memorize this, but I want you to notice how all of them have very small Ka values, all of these over here. All of them have a 10 to the power minuses, which is telling us that in this format, as an equation, our products are extremely small, and therefore we're getting very small Ka value. There is fewer product and more reactant. We can also interpret that for these Ka values, the reaction is moving in the forward direction. This is also telling us that the concentration of hydrogen ions is going to be lower than the weak acid ions. So because HA dissociates into hydronium/hydrogen ions, and we know that it's not dissociating enough, it's going to be very small. Okay. So here we have a bar graph comparing A and B. Let's look at A. So before dissociation, you have this much of your acid. And after dissociation, you see that they have all disassociated. Now let's compare that to B. You have your acid, and after dissociation, it's still the same, and only a very tiny bit of it is hydrogen and your anion in there. So which one do you think is a weak acid and which one do you think is a strong acid? We can see clearly that A is your strong acid and B is your weak acid. I'd like to talk about another previous concept over here. Okay, so why are we calling hydrofluoric acid a weak acid? It's because the bond between them is very strong and it's not easy to dissociate them. Now, a reason for that is that fluorine is highly electronegative and has a stronghold on hydrogen. Whenever an acid dissociates and gives away its hydrogen, whatever is left of it is our conjugate base, if you can recall the conjugate pairs. Think of hydrofluoric acid. If you somehow succeeded to break the bond between them, and you now have the fluorine ion, how would it behave, considering it has the highest ability to grab onto another ion very easily, or get attracted, or form a bond, or accept another hydrogen very instantly? So this is the reason why we say that the conjugate base of a weak acid is very strong. This is what this picture is telling us, that if you have a very weak acid, when it disassociates, it has the ability to be a very strong conjugate base. So whatever weak acid you have, it makes a strong base, and whatever strong acid you have, it has the ability to make a weak base. Okay. There are a few assumptions that we need to make in order to make our calculations easier for us. So we know that weak acids partially and barely dissociate. This allows us to change a few things in our ICE table and avoid using the quadratic equation or graphing calculators. So what we say is that whatever is the concentration of our weak acid at the beginning is our concentration that it has achieved at equilibrium. Remember, this only applies to weak acids because we know that the initial and final concentration of a strong acid would be completely different because they 100% dissociate. So their concentration of H plus ions is going to be very different. Okay, so this means that if we start with a 0.01 molar of any acid, any weak acid, then at equilibrium, its concentration would also be 0.01 molar. So how would we, or how can we change our equilibrium constant based on this assumption? So you have Ka, you have your products over your reactants. It is the same as this, my products over my reactants, because my concentration before and after of the weak acid is the same. And we also know that every time you have a weak acid disassociating, it is always going to disassociate like this, your hydrogen / hydronium ions and your anion. So whatever concentration you have of H is going to be your concentration of A. This is another assumption we make. And on the basis of that, we can just switch around our equation again. And this gives us an H. This is like this. I was unable to find a superscript that worked on an equation. So it would be like this, H squared over HA. And to solve that, all we would have to do is take a square root of Ka and concentration of HA. You would obviously be given enough information to be able to plug this in there, and to calculate the pH, you would take a negative log of that number. Let's practice a question over here. Calculate the pH of a 0.01 molar solution of ethanoic acid, given that Ka is 1.8 times 10 to the power negative 5. So I can confirm that this is a weak acid in two ways. First, that it is not one of the 6 acids that I have memorized. And second, the Ka value is very, very small. So I can tell that there was more of my reactants and less of my product. That's why I have such a small number. Okay. Now, there are 2 ways to solve this, and if you're familiar with both of these methods, you'd be able to relate them to one another. And knowing both of these methods is important because it is going to simplify all of these things for you. Okay, so first is just to take your equation over here. So you don't have your H concentration, but you do have your Ka, and you do have your HA, which is 0.01. So this is a simple calculation. We just multiplied the Ka with the 0.01, and we took a square root of that. You got your molarity. You took a negative log of your molarity, and you got 3.37 of a pH. Now, is this falling in the acidic range, this pH? Yes, it is. So we know that our answer is correct. Now let's look at another problem. Calculate the pH of a 0.01. I'm sorry, this isn't another problem. This is method number 2. Okay, so here we're going to write our equation. We're going to write all of our species down, this, water, hydrogen, and then our anion. I'm going to write an ice table over here. Now, the ice table does not have a column for water. It has a column for hydrogen ions and my conjugate base anions and my weak acid. So let's see. I have put in all of the molarities. This is my equation, H plus, my products over my reactants. Now, there are 2 ways to do this. Again, because you know that this is x squared, both of them are x's, I could have just taken it like that. This is what I did here. My concentration for CH3COOH, I'm going to pick that from here. Okay, so the 2 ways that I was talking about. First is that you can go with your quadratic equation and solve for x over here, okay? And second is to remind yourself, and I do this because I don't like the quadratic equation. So what you need to remind yourself about weak acids is that whatever the concentration is at equilibrium would be the concentration that is at the beginning of the reaction. So it is still 0.01. So all I did was multiply. I considered this as nothing because there is no minus x. The concentration is still 0.01. This is what I have learned about. So I would simply take the 0.01 to this, multiply it, and then get a square root of that. And this would be my molarity. Whether you use the quadratic equation or you do it my way, using this assumption, you would get the same molarity. And then you take a negative log of that, you get the same answer. Notice how in both the methods we're getting the same answer, okay? All right, now let's do another problem. Calculate the pH of 2 molar acidic acid. You have the Ka value again. You would be doing exactly the same steps. How about you pause this video right here and try this on your own. Okay, so I write my equation, I write all of my species, okay, and then I make my ice table. Then I go with my equation. So the concentration for my hydronium ion, remember that's also the hydrogen ion, is the same thing, is an X. And this is also an X. So that becomes an X squared. And my concentration for acetic acid is a 2.0 minus X. Again, I will use my assumption over here, and I would just not consider this at all because I know that my final concentration is the same as my initial concentration. If you want to go with the quadratic equation, please go ahead with it. It doesn't matter. And then you multiply this by this, you take a square root of that, and this should be your molarity. You take a negative log, and you get a pH of 2.22. Is it an acidic pH? Yes, it is. Okay. Calculate the concentration of all species present and the pH of a 0.020 molar hydrofluoric acid solution. You have been given the Ka. The steps are going to be the same. Please pause this video and try this on your own. So I wrote my equation, and I wrote my table here. I wrote my equation. I also want you to notice one of the things that I previously told you about was that whatever is your concentration of your hydrogen ions is the same as your M, as your weak acids anions concentration. So notice how it's X and X. I hope you are able to make this connection. And you get an X squared. Again, time for you to choose whether you want to go with the quadratic equation or just take the same assumption that the equilibrium concentration of our weak acid is always the same as our concentration at the beginning of the reaction. So it's totally up to you. You multiply this by that, you take a square root of it, and this is what you should get. This molarity, and when you take a negative log of that, you should get a 2.46. Is it acidic? Yes, it is. Okay. So let's look at something that is a little tricky. Not tricky, but yeah, I would still call it tricky. Okay. So what if you were to calculate the pH of a solution that had two weak acids? What is this asking you? It's asking you that who would be contributing more hydrogen ions to the solution, because that is what would raise the pH. Am I correct? Obviously, the one with the greater Ka. So whoever has a greater Ka, we're comparing this guy, hydrofluoric acid, and this guy. So both of these numbers are extremely small, but we can clearly see that HF is still slightly stronger than phenol. So what we're going to do is that we're only going to calculate the pH for our slightly stronger acid and not for the weaker one. It would be different, obviously, if both of your acids are strong, then that means both of them would be heavily contributing to the pH, and you would make the ice table and all of that for both. Okay. Now let's talk about percent dissociation. We know what dissociation is. Now we're trying to take a percentage out of it. We don't do this for strong acids because the dissociation is 100%, but we do this for weak acids. So how would you calculate? There is a simple formula. You take the concentration at equilibrium and you divide it with your initial concentration and multiply it with 100. So what happens when you dilute a solution? How does it affect your percent dissociation? This is a very important connection. That's why I made a different slide for this. And not only am I going to be explaining this, I will also be showing you math for proof. Okay. So what happens when you dilute a solution, or when you simply add water to it? There are two ways that the addition of water and dilution affects dissociation. Let's talk about the first one that you should be more familiar with, which is the Le Chatelier's principle. It tells us that a disturbance in the medium causes a shift to restore equilibrium. When you dilute a solution, you reduce the products, right? And in order to combat that, more of your reactants are gonna start making products. This is why your dissociation percentage would increase with dilution. Okay, another reason, adding water molecules into a solution allows the presence of water molecules to break further bonds of your weak acid. So more dissociation will occur, which means more of your weak acid molecules are going to be disassociated because of the presence of water molecules. Remember that when I say that dilution, the way it's affecting dissociation is not that it's changing molarity. We are talking about percentage here. Okay, so let's compare two situations, okay? You are going to calculate the dissociation of 1 molar of acetic acid and then a diluted version of it, which is 0.100 molar of acetic acid. Now, what I want you to do is that make a table, pause this video, make an ice table for a 1 molar acetic acid solution. So I just wrote all of my species in it. I wrote my table here, okay? I didn't make a column for water. This is for this. This is for this. This is for this. Okay. Now let's look at our equation. X squared over 1 minus x. Again, time for you to decide if you'd be using the quadratic or just remind yourself about weak acid assumption of concentration at equilibrium and in the initial. And then at the end, you should get this molarity, okay? Now when you calculate the percentage dissociation of that, so you take your amount dissociated, which is this, and you calculate it with your initial concentration, which is 1 molar, and you get a 0.423%. Now let's do a similar table for 0.100 molar of acetic acid. This is what you should get. The Ka value is obviously the same for both of them. You will get this number, this molarity. You're going to find a percentage of that, and you get a 1.34%. So this has only to do with the fact that you're changing your numbers, you're reducing your numbers, so obviously the percentage is going to increase. Okay, so I hope this makes sense, and in short, whenever we dilute a weak acid, the percent dissociation increases. This is the gist of what I just said. I will also write this as a bullet point. Okay. Now let's look at something similar, only that the information for the equation is a little different. What is the Ka of a weak acid? So this time we don't know our Ka, but we have our percent dissociation and we have our molarity. Okay. So here is my equation with all of my species in there. We don't know which acid it is. It doesn't matter anyway. We made our ice table. And then we have our equation here. We have the Ka value missing. Okay? We just have this and we have that. However, you do have your percent dissociation, which can also give you the value for x. In the previous questions, we were solving for x, but in this question, you can somehow solve for the X first and then the Ka. In the previous questions, we had the Ka, and from that we were solving the X. So all I did was move this around a bit. These are my numbers that are already given in the question. I moved my equation a bit, and I get, okay, once I move these guys around a bit, I take this to this side, and then at the end I'm going to multiply this by that. I hope that you know how to do it. At the end, you would get a value of X, which is 0.0081. And when I substitute the 0.0081 at both of these places, okay, I take a square root of this X and I get this number. And when I subtracted 0.100 from 0.0081, I get this number, and I divide it, and this is my Ka value. Let's focus on weak bases. Now, there's nothing different about how we're going to deal with weak bases as compared to weak acids. So the concept is the same, that the ionization of strong bases is, or their dissociation is 100%, but the ionization of weak bases is very small or partial. So let's look at all of these Ka values that we have for all of these bases, and notice how those numbers are extremely small. So this is also proof that even in a reaction where a base is ionizing, it would barely ionize. So this reaction tells us that ammonia has been dissolved in water and it accepted a hydrogen. It went from NH3 to NH4, and it has hydroxide. Obviously, this is not going to have hydronium, so we're not looking for hydroniums. We're looking for hydroxide as we're talking about bases. So let's look at how we're going to arrange our Kb value this time, because it's a base. We did the same steps. We put our products on top and our reactants at the bottom. We're going to make the same assumptions that whatever we have as our hydroxide is also our base. This is just a random base. It could be any base and hydroxide. So this means that if this is X, this would also be X. And we have our base that we began with. And this way we'd be able to solve for the concentration of hydroxide. Another similar weak acid assumption is that whatever is the concentration of your base at the beginning of the reaction is the concentration of your base at equilibrium, because it barely partially ionizes. So in other words, if we started with 0.01 molar of ammonia solution, we will assume that even at equilibrium, it's as 0.01. Okay, so this is what we just talked about. I can simply replace them here, and it would be my OH square over NH3. Okay. Let's solve a problem over here. So what is the pH of a 0.40 molar ammonia solution? And you've been given the Kb value. You're always going to be given the reactions in order for you to know whether they are acids or bases, as in, are they accepting a hydrogen or are they giving it away? So let's look at our general equation for the equilibrium of weak bases. There are two ways we're going to be solving this question. First is using this because I can, and the second would be the ICE table. So I'm going to solve it based on this. It's just going to be simpler because I have all of the information. So all I did was switched my equation around a bit. I did have the molarity for ammonia, and I do have the KB value. So all I did was take it to the other side of the equation and took a square root of that, and this is how I have my molarity of hydroxide. We also know from section 8.2 that the concentration of hydrogen ions or hydronium ions multiplied by the concentration of hydroxide ions always gives us this number at room temperature. It's okay if you've forgotten about it because this is on your formula sheet that you will be provided with during your exam. So because I have all of these values, all I did was switch the equation around. I just did a 1.0 times 10 to the power negative 14 divided by hydroxide, and my hydroxide is at 2.7 times 10 to the power negative 3. I get this number, which is my molarity for hydrogen. Okay, and then I have my concentration. I take a negative log of that, and I get an 11.14. I hope that this equation made sense to you right over here. That all I did was that because in the question it hasn't given me any other temperature, so it means I'm going to assume that it is room temperature. And at room temperature, my K value is this, and I figured out my hydroxide value. So I had everything from the equation. I just didn't have my hydrogen concentration. So this is why I did all of these things. So my answer, my pH is 11.4 for ammonia solution. Does this fall in the basic range? Yes, it does. Okay. There's another way that we could have gone about. So what I could have done was taken the hydroxide concentration, which is a 2.7 times 10 to the power negative 3. I calculated that, and I would have taken a negative log of that. So now I have my POH. There is another connection that you should be able to make between POH and pH, is that POH and pH combined always make a 14. So I can simply subtract it, and again, I would get the same answer as that. Let's look at another question here. Calculate the pH of a solution of 4 molar methylamine, and I have been given its K value. Obviously, you're not expected to know whether this is accepting or donating, so you will be given other information in regards to it. So here are all of my species. I can see that this went from H3CnH2 to H3CnH3 ion, and water is just left as hydroxide. I'm going to put up my ice table. 4 for this, zeros for that, and then an unknown X was deducted, unknown X and all of that. Okay, let's go further. I'm going to now take my equation. So I just wrote this, but obviously in this case you can also take this as these two guys as the numerator. It would still be the same thing. It would still be the same thing mathematically, because we know that whatever is this ratio is also this ratio. So it is a 1-to-1 ratio. It is, both of them can be considered X. So that's why we can just move this equation around as OH squared or X squared, whatever. So X squared over 4.0 minus X. This is my KB value that I've been given in the question. Now we're going to ask ourselves the same questions. Do we want to do it the quadratic way, or do we want to do it our equation way that tells us that whatever is the initial is the equilibrium? So we could just not use this. Just multiply this by that, take a square root, or if you use the quadratic equation, if you want to stick to how you did it in unit 7, it's totally up to you. And the value for your x should be 0.042. You take a negative log of that, and you get a 1.38 as your pOH. And you can easily calculate the pH from that, which is at 12.62. So does this fall in the basic range? You always have to make sure at the end of the question. Yes, it does. Okay. So what is the pH of a 0.150 molar solution of ammonia? You have been given the Kb value. And then you have another question that asks you to calculate the percent ionization of a 2 molar C2H5NH2 solution, and you've been given the Kb value again. So what I want you to do is that you pause this video over here and you solve both of them. You are familiar with calculating the pH thoroughly, and you are also familiar with calculating percent dissociation for weak acids. It's called percent ionization for weak bases. It's the same thing. It has the same steps. The answers are given at the bottom of the slide. You know, when you're not in full screen, it shows you the notes. Please match your answers to that. It's the same as dissociation. Okay. All right. Now, before we end 8.3, I just want to make sure that you know how to use and how to pull out these formulas when needed. So this is your main acid equation, your acid equilibrium, Ka. You have your, because acids always give away hydrogen ions, and your conjugate base over your over your acid. And then the pH is a negative log of your hydrogen concentration. Also, that a P of Ka is just a negative log of Ka. Then you have the same equations for base equations. It's important that you know that pK is just a negative log of pK. And then your general equations, all of these, especially these, are given to you. Just make sure, I'll make sure these are too, but even if they're not, you know how to calculate, how to write the equation for the K value. So I would expect you not to know this 1.0 times 10 to the power negative 14, but I expect that you would absolutely know how to do this. And that pH and pOH makes a 14. Also, the inverse of 2, 3, 5, and 6 are these values. So the concentration of hydrogen is at 10 to the power negative pH. Because you guys are better at math than me, I'm expecting that you would know what this means. But point is that it's very important to make a connection out of these. So what about polyprotic acids that donate more than one hydrogen? So until now, we have been dealing with acids that only donate one hydrogen. And in AP Chem, you are only asked about monoprotic acids. So you don't have to worry about that. You don't have to get into the depth of polyprotic acids. But you are tested on your knowledge about the different K values that a polyprotic acid can have. What I mean by this is that if you have a polyprotic acid, this means that it donates 3 hydrogens, but it doesn't donate all 3 hydrogens in one go. It happens in 3 different steps. And for that very reason, a polyprotic acid would have 3 different K values. In a question that asks you or gives you all of this about polyprotic acids and you are asked to calculate, you are not going to calculate for all of them. So this is the information that you must know, that you won't be doing it for all of them. You would only be doing it for K1, as in the strongest K value out of them all. And it's always the K1 value that is the strongest of all. The other hydrogens take a while to disassociate, so we don't look into that. That is not what decides the pH of a solution that has a polyprotic acid. It's the K1 that decides the pH of a polyprotic acid solution. So you're not going to look at any of these. You're only going to look at your K1, and you will do the same steps as you previously did. Okay, this is another example. You have H3PO4, so it donates hydrogens in 3 different steps, one by one, but we're not interested in any of these. We're only interested in the first hydrogen dissociation, which is this one. So we're not going to even look at them. Okay, so that is it for 8.3. Now your next step after this is hop on to Michael Farabaw's packet and videos. You will solve them on your own. You will also play those videos in order to note down things that you haven't picked up from my lecture, or things that you just needed to be reiterated. Once that is done, please hop on to the only, I think, 4 or 5 questions that you have on your older packet. Also, I've noticed that none of us have watched any of the AP Classroom videos that I recommended in my previous lectures. I hope that you will be on board once school resumes. I am not going to be slowing down because of Ramadan, because these last couple of weeks are the most crucial ones. We also have a mock, and these topics are going to be included in them. Thank you.